Okay, here's part two of 1E. So we're going to talk about cumulative relative frequency graphs. So these work really nicely with percentiles. They definitely are connected with the line segment to form a graph. This looks like one. You can see the max there is 100%, and the lowest there is 0% on the left. And this is president's age when they took office. And it's actually just a really nice way to represent, but it's a little weird at first. So the point 40 comma 0, just to understand what those points mean. So 40 is the age when a president took office. 0 signifies 0% of presidents took office at age 40 years old or younger. So every president we've ever elected has been more than 40 years old. It's kind of interesting. So if you look at that point at 45, so the next point on the graph that's kind of identified, 45 comma, looks like, I guess 4.35 is what it says, signifies that 4.35% of presidents took office at the age of 45 years old or younger. So there were maybe a couple, I'm not sure exactly how many, but we know the percentage is 4.35% were 45 years age or younger. So again, percentiles is that age or younger in the case of percentiles. 80, the point at 80 means that 100% of presidents so far took office at the age of 80 years old or younger. So we've never elected a president who was more than 80 years old, right? So it's cumulative. So it just keeps on going up until it gets to 100%, right? So when Barack Obama, he was 47 years old. Was he unusually young or old when he took office? So that's in between, but I think it's kind of young. So to find that, so you have to find his age. By the way, his actual age is 47.463. So I'm guessing he was born in like maybe May, it sounds like. Just looking at the 0.463 there, then draw a horizontal line from this point to the vertical axis. So you find 47 points, so you draw that line. You can see that kind of actually a vertical line there, and then when it hits the graph, you draw a horizontal line, and it looks like around 11 percentile there. About 11% of the first 46 US presidents took office by the time they were 47.463 years old. So Obama was fairly young, but not unusually young when he took office. So unusual in stats is 5% or less typically is what we call unusual. So 11% is not quite to the state of unusual, but he was on the young side for sure. By the way, I've met President Obama. Estimated the 65th percentile of the distribution. So here now you would start on the left-hand side, right? Because that's a percentile. That's what those are. Cumulative relative frequencies are percentiles. So you start on the left and you draw the line horizontally till you reach the graph and then draw down. And it looks like the age when you took office is about 59. So the 65th percentile is about 59 years old. What happens when you add, so this is now transitioning, not to percentiles and cumulative graphs, but transforming data. This is something we do, and they'll definitely ask a few multiple choice questions about this. So if you have a set of data, like here this data is about test scores, or 50-point AP stats test. You see a lot of folks were 30 or above, but you had some folks down there. Wow, it's rough. It's rough down there. Okay, so the data looks skewed left, but you get all this data values, right? So if you added a number, so let's see, what happens when you add 5 points to each person's test scores? Because sometimes some teachers will even curve that way. They'll say, well, I'm just going to add 5 points to everyone's score. So what would that do to the graph, to the so forth? So I like the picture of it. So you can see the graph just kind of moved over 5 points. The max is now 53-ish. The min is now 17-ish instead of 12-ish. And So everything just kind of moved over. So what changed as far as the measures of center and so forth? And so you can probably see that the mean and median are going to move up 5 units. The measures of center are going to change, right? The new center is to the right 5 units from where it was. But the measures of spread or variability, do you think they changed at all? It looks like the same width. The range looks to be the same. I'm pretty sure the IQR would be the same. Standard deviation would be the same. So it changes adding a positive number or subtracting. Changes the measure of center at the same amount, but does not change any measure of variability. Range, IQR, standard deviation do not change at all. The shape doesn't change. The shape was the same. It was still skewed left. So it doesn't really change any of that. Here's the actual data up here. If you want to see the adjusted, you can see that the mean has gone up by 5. The median's gone up by 5. Q3 has gone up by 5. Q1 has gone up by 5, but the IQR did not change, right? Q3 minus Q1 is the same. Max minus min is the same. So the measures of variability or spread did not change. Standard deviation did not change. What happens when you multiply or divide a number or multiply by a fraction a number of all the test scores? So if you multiply all the test scores by 2, maybe, again, it'd be a weird curve because the top of the data is really going to be affected there. So let's see what would happen. So, wow. So now the top person got um, something seems funny there. Oh, the adjusted. So they took the adjusted score, which was 5 higher. I was trying to figure it out because it's over 100. I was like, what's going on? The adjusted score was the one that was 5 higher. They doubled it, so now that's way up there. So the shape didn't seem to change, but the variability changed. I don't know if you can see, but the doubled is a lot wider than the adjusted there. Um, so it does seem to affect everything except for shape, I think. So I like how they just kind of pair it out. So they say, okay, multiply does change the mean and median by that multiplication factor. It does change all measures of variability, range, IQR, standard deviation. It does not change the shape. So adding or multiplying does not change the shape, but multiplying does change both as far as measures of center and variability. I like how they classify it that way. That's how I want you to think about it too. Okay, so suppose all the temperatures are converted to Fahrenheit. So this is currently Celsius, which we don't really know. If you've ever been to Europe, I just went this last summer and hard to convert in your head. Okay, so what shape would the indoor reading in degrees have? So what's going to happen to these measures of spread and measures of center here? So uh, if you think about the 9/5, so that's multiplying. So the 9/5 is going to affect both measures of center and variability, whereas the adding 32 should only affect the measure of center, should not affect any kind of measure of variability. Same shape, so multiplying and adding don't affect the shape, so it's still going to be, roughly symmetric and single peaked. That's right, so none of that changes the shape. So what's going to happen to the mean? So you can actually just take the mean as it was, the 8.43, multiply it by 9/5 because multiplying does affect the measure of center, and add 32, and you will get the new mean of 47.17. But for standard deviation or any measure of variability, you're only going to multiply, you're not going to add, right? So standard deviation, it's going to be 9/5 times the current standard deviation, 2.27, and you do not add the 32. It's not going to affect, so you don't want to add that to that. Okay, you're done with the lesson. Let's just try a few practice problems here. So this is another cumulative frequency. Americans love their pets, but owning a pet comes with a variety of costs. I think that's probably true. The cumulative relative frequency graph summarizes the average yearly cost of owning a dog. Okay. So the average yearly cost to own a dog in Massachusetts is wow, $2,702. Is this an unusually high cost? Does it really cost that much to own a dog? It's kind of incredible. So I don't know. Does it? The average yearly cost. So how would you find that? So you could look at what 100% is, or oh wait, let's see. So the yearly cost, 2,702. So 2,702, if you find that on the x-axis there and go up to the graph, you can see it's very, very close to 1 or 100%. It's at the 98th percentile of the distribution. Based only on 2% of states have a higher yearly dog cost of ownerships, Massachusetts is an unusually expensive state for dog owners. If you want to find the median dog owner cost, what you want to do is go to 50 percentile. They didn't ask this question, but I think it's a good question. No, I'm like, well, maybe Massachusetts is really expensive. So if you go to 50% and go over to the graph and go down, I'm eyeballing it here a little bit, but about $1,700 a year is what you would expect the median cost to be. So median is very easy to find with a cumulative relative frequency. The mean is not so easy there. I'm not sure we can find that with just this graph. But median is always 50% here for this. So $1,700 is still a lot. The second question says, estimate the third quartile. Oh, so what it's asking you to do is third quartile is 75%, right? So you start at 75%. I'm kind of eyeballing it here, but you go over and you go down around 1900. So yeah, that's what they said actually. So 75%, go over to the graph, go down, and it's somewhere in the $1,900. So the average yearly cost of dog ownership is less than or equal to $1,900 in 75% of US states. So there's a pasta place, it's an authentic Italian restaurant that makes its own pasta. The rigatoni pasta is so popular that customers buy 32-ounce boxes of the pasta to cook at home. The employees who fill the boxes aren't perfect, however, so the actual amount of the box varies. It's true. To check their work, so he selects 50 boxes at random for 1 week's production. The dot plot and summary statistics are given below. So you can see 32 is, I don't like this. It looks like they may be shortchanging their customers a little bit because it looks like more than half of these are less than 32. He's worried that they were being underfilled. So he adds an extra 0.5 ounces, right, to the 50 boxes. So they wouldn't feel cheated. So calculate the mean amount of rigatoni for these extra pastas will the customers be satisfied. So we know the original mean was listed as 31.7. So if you add 0.5, that's going to be 32.2, I believe, right? So 32.2 because adding does do that. So now the mean at least is above 32. So the mean amount is 32.2. So that's good. I'm a little bit happier with that. Boy, there's one low outlier. I'm really not happy if I get that guy. Because some customers had recipes that used the metric system, the refill boxes were relabeled to show the mass in grams. Oh, so they had to convert this, right? So to convert it to grams, it says that 28.35 grams is 1 ounce. So you're going to multiply this number, right? So multiplying affects both the mean and the standard deviation, right? So if you start with the 31.46, which is the 75, the peak is between 9:10 and 9:15. So they basically took 31.6, which is so the peak is between 31.6 and 31.8. So they took that interval and they converted it, right, by multiplying and adding, right? So the mean, so you have to add and multiply. So you have to add first, by the way, then multiply by the 28.35 to get that interval will go from 9:10 to 9:15. The mean would change, So the mean you both add and multiply, add first and then multiply. But the standard deviation you only multiply, right? Um, so I don't think they had to do that first part. They took that interval, but it's just showing you just how to do it there. But that the mean is standard deviation, but the shape, of course, is going to be the same. It I guess would be skewed left. I think there, yeah, skewed left. Um, but it's just the mean and standard deviation. How do they react to adding and multiplying? Of course, you add or subtract first, then you take that total and multiply. Make sure you do that. That's the lesson for today.